Hey, how's it going, everyone? Today we're going to be talking about linear regression. So this video is just going to be an intuition behind linear regression. And following this video, I will be posting another video where I will be implementing linear regression from scratch in Python. So before we begin, I'm starting off with linear regression. This is going to be a series of lectures where I'll be giving you an intuition behind various machine learning algorithms. But the reason we are starting off with linear regression, and then after that I'll be talking about logistic regression. The reason we are starting with these two algorithms is that they're very, once you learn many of the concepts involved in these algorithms, such as cost function, loss function, or even gradient descent, these fundamental concepts are then applicable for, if you want to learn how neural networks work, right, in the future. And of course, as we are advancing in this course, you will be encountering these concepts over and over again, especially in deep learning. And when we look at how neural networks work. So let's just get started with linear regression. So what is linear regression? So linear regression is an algorithm that tries to predict a number that is continuous. That is the simplest definition of linear regression that I can give you, right? It simply tries to predict a number that is continuous. So given set of independent variables, your target variable tries to predict a continuous value out of infinitely many possible values. So for the sake of simplicity, let's say you have some data set, right, in which you have values for x and values for your target variable y. This is some data set in which you only have one feature, right? And for example, every value is a scalar value, right? So it basically means that every sample here, for every sample, x is a scalar value. That's what I'm trying to say, right? And let's denote each row here as an example, right? Some people call this as a sample. I'll just call it an example, right? Let's say we have m examples, right? And let's just say we try to plot this, right? This is an x-axis and this is our y-axis, right? For example, for 200, let's say 200 is right over here. It's really zoomed out. Okay, and for that we have a value of 0.5, let's just say, and then you have 450, right? And for 450 you have some like right here, right? And let's just say for each of these x values, I'm just going to plot some arbitrary points, right? Just for the sake of example. All of these points belong to your data set, by the way. So let's say all of these data points belong to your data set, right? Now assume you have a new value for x, for example 3225, right? Just a random value, right? Now you want to try to figure out the value of y, right? But this data point does not exist in your data set, right? So what can we do about it? So one thing we could do is try to learn some pattern in this data, right? We could try to fit a line to this data, right? That tries to capture this data as well as possible, right? So you might argue this is not the best line to capture most of the data because majority of the data is like this way. So you could kind of construct a line, for example, that is like that, right? That is like that, and that captures more data than the previous line. But I mean, you could just spend most of your day trying to come up with the best fit line, and that is not the most efficient way to go about this. So one thing we could do is to come up with a formula for a line, right? And you might remember this from your college algebra days. Let me just write this down. So for the formula for the line, um, I'm just going to write this as a function uh, as wx plus b, where, so I'm just going to write where, for the sake of simplicity, w and b are scalars, scalar numbers, right? They're scalars, right? They're not vectors, right? Because we're only dealing with one value of x at a time per example. So this should be familiar to you as mx plus b, right? Where m was the slope of the line and b was the y-intercept, right? Let's just visualize this. So I have the exact same formula plotted in my GeoGebra calculator, and I have some sliders for w and b, and as you can see, if I increase or decrease w, this actually handles the slope of the line or the steepness of the line, right? And as I'm playing with the value of b, it controls the intercept where the line intersects the y-axis, right? So basically going up and down. And these two values are the only two values you need to define a line, right? So what I'm trying to kind of find is the value for w and b. Once we have the optimal values for w and b, we will have the best fit line. But how do we find the values for w and b, right? So that's our goal. We want to find the best possible line that fits this data, that captures this data very well, right? For example, if we try to predict that this is the best fit line, okay, and we try to say, okay, if this is the new data point, 225, we just look at this line, right? So this would be right here, right? And we just look at the corresponding y value. So let's say we have some initial values for w and b, right? How do we determine? First, we need to have some sort of measure of how do we determine whether the line that we have now just came up with is, how is that a best fit line, right? We need some sort of measurement, some sort of quantification that tells us how well your current line fits your data, right? So let's think about this. One thing we could do is to denote each of the points on the line as y hat, right? And the actual values for the points as y, right? So for example, we could say, okay, this value right here for this x value, right? This is y hat, but the actual value is this one, right? Which is the value of y. But you can see there's a huge difference between the predicted value and the actual value. So what we could do is to compute an error, which is basically the difference of y predict and y, right? But we don't want to kind of leave this like that for all the values, because then you could have negative numbers here, right? And we want to compute an error as a positive number. So what we could do is to compute a square of the errors. So this would be kind of do this for all. So this is a kind of discrete mathematics notation for all, I guess, x, right? For all x, do this, right? For all of these points, compute y hat, and then subtract that, or rather subtract actual value from y hat and square it, right? And this would be your total error, right? Your total error, right? In machine learning, we call this total error as the cost function. And we denote this as J of W and B, right? J of W and B, which is equal to, so we know how to compute an error between individual points, right? So let's say we're dealing with ith example, right? We're dealing with ith example. So this is y hat superscript I and y superscript I, right? And we want to take the sum of all errors of all points, right? And we're going to do this from I equals 1 to, let's say we have the number of samples as m, right? So the number of examples here is m, right? And then after we do that, we also want to divide this by m, right? The reason for that is if the number of samples increase or the number of examples increase, you don't want this cost to kind of shoot off, right, and become a very large number. So you want to kind of take an average of this sum. In machine learning, we also use this 2 and divide this by 2m, and this is just so that when we take a derivative, and we'll see that later on, the calculations become neat, right? So that's why we have this 2, although this has negligible effect on the value of the cost, right? So this is our cost function, right? Now this cost function is actually dependent on the value of w and b, right? And that makes sense, right? We want to find the optimal values for w and b, and depending on what values you're choosing for w and b, you're computing the cost, right? For some values of w and b, the cost might be lower because your line actually fits the data very well, but for some other values for w and b, the line might not be capturing your data, right? And in that case, the cost would be higher, right? So if this is not obvious that why are we inputting w and b, I can expand this formula as 1 over 2m summation from I equals 1 to m, right? And what is y hat? Well, y hat is basically fwb of x superscript I, right? But what is that, right? What is that? If I expand that out, what is that? That is basically w x of superscript I, right, which denotes a particular sample, right, plus b, right, minus y, and that is squared, right? So this is your cost function. Okay, so just to visualize this cost function, let's assume the variable b, or the model parameter b, is a constant variable, right? So let's assume we just fix this variable, right, as some constant, right? Let's say b is equal to 1 or something, right? It could be any value. I'm just fixing the value of b so that we can only focus on only one parameter w, right? So if you plot the function j, right, with respect to w, so let's say this is the w axis and this is j of w, right? You'll see that this is a convex curve, right? This is a convex curve, which means this will always have a minima, right? And the goal is to actually get to this minima, right? So this is the least possible cost, right? And this corresponds to this w value, right? This w value, let's call it wi, right? This this value, if we were to input this to our main hypothesis function, this will actually give us the best fit line, right? What if we have multiple features, right? Right now we only dealt with only single value of x. For suppose we have x1, x2, x3, and of course all the way up to xn, right? And then you have the target variable y that is dependent on these all of these independent variables, right? And of course you could have the data set that has all these values, right? You will have all of these values, right? But the concept remains the same. For each of these input values, you would have w1, you will have w2, you will have w3, right, all the way up to wn associated with all of these input variables, right? And let's represent this as a vector, right? Let's represent this as a vector, right? We could write this as w1, w2, all the way up to wn, right? And we can also represent these set of values as a vector, but we'll take a transpose of it, right? So for example, if I could write x1, x2, all the way up to xn, right? But at the end I will take transpose of it and then take the dot product, and this will be the same as wx, right? But instead of multiplication of two scalar numbers, you're taking the dot product and then adding on this b term, which is again, it's a scalar number. This is never a vector, right? This is just a term that is added in the end. So the dot product will be a number. So the general formula that we have is actually, so we'll denote w with this cross on top of it, which represents or indicates that it's a vector. We'll also represent x as a vector, right? And the general formula for that, for any number of features that we are dealing with, is x dot w plus b, right? So that's it. In the next video, we'll be talking about gradient descent, one of the most important algorithms in all of machine learning. You can even say that gradient descent is, in and of itself, what learning is, right? What we have discussed so far is not really learning. We've discussed the essential, I guess, mechanisms. For example, a mechanism for measurement of the error between predicted and actual values, but we haven't really figured out how to learn the optimal values for w and b, right? So that's what the gradient descent will allow us to do. It will allow us to learn the optimal values for w and b. So thank you very much for watching this video.